Rest of this, as much as we can of this unit. If I need to collect the beautiful twirling batons, I can. So, does bivariate data always deal with linear? Can it be any other forms like quadratic, exponential, cubic, and so forth? So, if you, I don't usually get a chance to cover it in my regular Algebra 2 class, but if you're in my advanced Algebra 2 class, I actually do talk about this. So, most data is actually non-linear at all. Most data looks something like this. Not this specific case. But does that look traditional linear?
No.
No. What shape does that remind you of? Probably an exponential. So what you can do, and it could be quadratic or exponential, but what you can do is, if you think that looks exponential, and we'll actually look at a lesson of this that goes in more detail, but we're not going to do the exploration that I normally do. You can take a natural log of all your y values. Because if this is exponential and you take the natural log, what's it going to do to the overall pattern of the data? Okay, so I was saying, if I have e to the x, and I take the natural log of e to the x,
Cancel it out.
these cancel and I'm left with
X.
which is what type of function?
Linear.
Linear. So what we will do is, if we say, hey, I think it's exponential, we'll take a natural log, and so now it looks something like this. Looks more linear. Those would not be the same at all. But the idea is that it is way easier to fit a line to data than to figure out what that curve is. And so, can it be nonlinear? 100%. But what we will do is we'll linearize it and then use that linearized data to get my least squares regression line, etc. Okay? But Ms. Kowalski and I are going to move on from there. That's the only question we had, I think.
Wait, how do I pull the thing up onto the calculator?
Is it not on your calculator already?
No.
Are you logged in?
1 second. I don't know what that is.
What's up? Say again? Okay, let's focus on the stats right now, though. Yes,
Is that an amazing question?
it was a good question. You can get candy later, not right now. We got it. Hey, quick question. Show of hands. Who has a calculator at home?
Not at home, I have one in my bag.
You have one with you.
How do I charge it?
This is my backpack.
You bring it back and you plug it in.
Oh.
Okay, quick show of hands. Who has one that they have at home that is not here? So Michael, Sanaya.
Not or
So are your calculators just missing?
Yes, but that's two. But you have one. 3, 4, 5, 6, 7. And then you had one as well. So 8. So that's at least 8 of them that are accounted for.
okay, so that's still
But yes.
missing.
Well, I was missing 4 or 5 at the beginning of the semester because high school students. But I just need to know how many to.
Someone stole $100 calculator from you?
Bro, what?
Well, I can
Yes.
think of
Let's do this. Pause and listen, okay?
Yes, sir.
Tomorrow, I need everybody to bring their any and every calculator that they borrowed. I know one person accidentally borrowed 2 one time. Everybody bring the calculators they have borrowed so I can get a count and figure out how many new ones I need to ask admin to buy for me. Yes?
I will not be here tomorrow because I have a doctor's appointment, but I have one, so just.
Okay, email me to remind me. Thank you.
How do I
Alright.
do the calculator?
And there's one
Oh, never mind, it has squares on it already. Okay.
Right, I was like, y'all, if you still have the same calculators yesterday, you still should have squared up. As a reminder, mock exam, we said 11:30 for food, start time at 12 o'clock. Today we're going to finish looking at correlation. No, that was yesterday. Today we're going to finish looking at least squares regression line or residuals. And we will hopefully get to the horsepower lab today, which is why we all brought comfy shoes to run in, Sanaya. Serena.
I forgot. It's okay, I got this. Approximately.
Oh no, she's gonna have to.
Alright.
You can run in Converse, right?
She can
Yeah.
Yeah, you can really run anything.
So remember we're doing squared up.
That shit is so wet.
You ready to?
You have to go up.
So guys, y'all need
He was
calculators.
outside.
Excuse me. Hey, focusing on stats.
Yes,
Y'all
sir.
need your squared up task out, and you need this sheet out so that we can talk about some really, really, really important concepts.
Yes, sir.
Which sheet is this?
This is the one that says squared up. It's the next sheet in the packet.
You want us to open it?
Yeah.
Yes.
Alright, so yesterday, we worked on trying to find, it was the, analyze the add movable line. Does everybody already have a movable line on there?
Yes, ma'am.
Yeah.
Did we move the line to get it as close as we can?
Yeah.
Yeah? Beautiful. Alright, so if it's not already pulled up, go to Analyze, Residuals, and then Show Residual Squares.
Hey, pausing for 1 second. Did someone leave theirs in here yesterday? Because there's a little bit of writing at the top. And I think it was at that desk, the Jacks. I don't remember 100%.
Michael was, I think, was it Michael?
I have mine today, so it
Michael
can't
and
be
Jay, but
mine.
they none of them have theirs.
So I'm
Whatever.
guessing.
Jaden doesn't have anything
What is
else,
it?
so it might be Jaden's. I'm gonna assume that
Oh, yeah.
it's Jaden's actually.
Okay, well, I might be able to do
Yeah,
that.
yeah,
And I'm hoping
If you are missing other things later, we'll find it. Alright, we gotta go.
A square will appear at each data point, sin of the square is equal to the value of the residual. Examine the data point,
I had this one too. Yes.
examine the data point such that the year is 1950. What is the residual for this data point? And then interpret it in context. So we all may have different values there, because all of our lines are different. What is, 1950? Can you hover it or no?
Yes, one thing I just realized that I don't think we've actually talked about how we write this equation yet, have we?
The line
No.
bar thing.
So, one thing to be aware of here, what is m of x also, like what's another way to write that? 1, right? But I need us to recognize that that's describing this line. Is that what the y variable is for every single data point?
No.
No. So what we use is we use a little hat here. Y hat is our predicted y value. And traditionally in statistics, we don't do y equals mx plus b. We do a plus bx, where what is a going to be? The y-intercept, right? There's no variable with it. And b is my slope. So like for me, at least right now, y hat is equal to negative 492.7 plus 0.286003 times x. I brought that up because what we want you to do is find a residual, and how do you calculate a residual?
I'm confused.
Well, if we look here, it defines what a residual is.
And it also tells us on how to calculate it.
Yeah. I'm just literally asking, what does it say for residual?
The actual value minus.
Actual value minus
Predicted value.
predicted value. Hey, any guesses what I need for my predicted value?
Our,
Value?
our line,
The what?
The line of the.
Which y?
y hat.
I mean, hat.
Remember, if I want a predicted value, I need y hat. That's why I was bringing this equation up. So Sprig, whatever the actual y value is, and then find the predicted value. So I'll come around and support you, you work with each other, but you can actually hover over these data points. So notice that's what year? 1940, and the actual expected lifespan in 1940 was what? 63.6 years. So go to one more, there's 1950, and what's the expected lifespan there? 68.1. So if I want the residual, I need the actual value there, and I need to subtract the predicted. So
Where's the predicted?
You plug in the year for your x, right, because that's what our x is, and then calculate your predicted. You use the line you created yesterday.
let me point, this is another way to say it. The predicted life expectancy, I always like to put variable context in here, is equal to negative 492.7 plus, what is that x representing?
1950.
Well, 1950 is just one of the options. What is x?
The variables.
The variable year. So if I want the predicted life expectancy, what do I need to substitute in? the year. So substitute the year 1950 into whatever your equation is.
Wait, what if I don't have full 950?
You probably won't. We
all have
probably
different
won't have
lines.
the same. Everybody has
okay.
different lines.
Okay.
The whole point is that you are using your model. So models would be different, okay? You need to actually create a scatter plot. Ms. Kolsky, can you help us create a scatter plot? So here's your issue. Hold on. Okay, so you need to, so when you're on the
So it
edge
goes
here,
there.
it's rotating it, okay? Which is fine, but you need to be on this side because you
Goes
need to
there.
rotate this. But your y-intercept's off.
Yeah.
So that's why it's acting like that. Okay?
Here,
So
and then what goes on
what does the
Y?
problem say? So to go to the center, it's gonna let you translate it down. And now I'm gonna have to rotate it.
So hit menu, actions, or, and, back,
Okay,
analyze.
so now, see how that's a little bit closer to the slope of that line?
Add movable line.
Now I'll say this, you're not gonna have to do this very often. There's a reason why I had to do this though.
And then you can move this line around, over here, click on
So
it.
now it looks like your y-intercept's probably close to right, but you need to change your slope
You're gonna move it
to,
fit better.
to hit those data points as well as possible. Now, I would
Menu,
just go from there
analyze,
and
I'll be
find
right
this
there, Nate.
information.
7,
Okay.
show,
What did you say for that one, Peter?
The distance between the predicted and actual value of the lifespan for, would you say like a person in 1950 or like all people born in 1950?
I think it's an average, so that's fine either way. But I will say, it's not just the distance. I want us to think right here. Let's look at number 3, so if you can pause for a second. If a data point is above the regression line, is the residual going to be positive or negative?
Positive.
Positive, right? Because the actual value is larger than the residual, right? So it's going to be positive. If a data point is below the regression line, the value is going to be... So what does the fact that that residual is positive tell us?
It's above the line.
So there's two ways you can interpret it. You could say that the actual life expectancy, knows context, is 3.09 years more than predicted, or the predicted is 3.09 years less than the actual. But notice it's comparing the actual and the predicted. It's telling if the residual or that distance is more or less. So the actual life expectancy, yeah. EXPECT, expect,
yeah,
I spelled it wrong too.
is 3.09 years more than what was predicted.
did anybody get a negative?
That point was pretty high, that,
Yeah.
I feel like getting negative would be bad.
It's fine to be negative, there's some data points that will be.
I know,
Oh,
but
yeah.
it's like,
I ain't talking about based on like where that point, it
I got
was.
you, yeah. I will point this out, a common mnemonic device that a lot of teachers use, you don't have to, but this helps, is a residual. So AP, actual minus predicted. So just using that AP acronym.
Rap.
But what I
Right.
prefer is I prefer actual minus predicted this way. This helps me remember it's the actual Y value minus the predicted Y value. The Y hat tells me predicted, which Nate is how, that's how you wrote it earlier, right? So actual Y minus the predicted Y. That's how I would recommend doing your residual.
Alright, so, now, but did we already do the least squares?
They haven't actually played around with it to make sure it's the smallest sum of squares they can get, yeah.
We do have them already on there, are squares correct?
Everyone should, yep.
So, you guys are going to move around your line again to make, on your graph, go ahead and pull it up. There is the sum of squares right below our equation. You're going to make this number as small as you can by moving this line around. Does that make sense?
My challenge for you is to get it under 50.
Hey, Mr. Kenny.
I think that's about the lowest I've got.
43 is crazy.
So, but now I'll start answering those questions.
I don't think my
So get it close.
I have 47.
Wait, what's the?
So remember, you can change slope and y-intercept, but focus right here. So now, this answer was the smallest value you can get. You wanna know something cool? Control C, just like a computer.
I'm sorry,
What are you freaking out about? Hold on. hit escape.
You might have to switch the slope around because mine wasn't going.
You gotta remember that if you put it in the center, it allows you to change the y-intercept.
Oh my gosh. This
But
thing
if
is
you
so
put it
hard to
towards
figure
the
Yeah,
out.
this really annoys me
And-
on my calculator.
It'll let you rotate
I
it.
wish I like
What?
Serena. Why do I talk?
Were you gonna pull up the data?
Hey guys, I need y'all to move on to the next question,
Are you joking?
No.
okay? The priority is understanding what a least squares regression line is, so you can start to answer the rest of the questions at this point.
So what I do is like, I can't. It's like,
Oh, you can't really tell the difference? Well, so actually, that's your new model. That's the least squares regression line right there.
Wait, how do you switch from the?
so how to know which one's which?
Oh, 1, 2, I would just count those
What'd you
on,
get?
and then, trying to remember. So, 2000 through 2004, so 5 data points are below there. So that's 5, 6, 7.
How do you switch?
1, 2, 3, 4, 5, 6 above, and 2.
I get it. I got 50.
Yeah, how do you switch to?
Mr. Kenny, I did.
Can you send me the data again? I can't.
He don't even
I got
hear,
one.
like, I
Yeah.
just put it like it's on.
Let me go browse.
Yeah, I was looking for
That's not what I want.
Like I'm scared because every time I click away,
Yeah.
It won't go.
Wait. Wait.
So you can also move it, the line.
Yep, I'll resend it to you.
Yeah, because I can, like after I got
Oh,
out,
yeah,
I can find it. Oh, nice.
You can also, yeah, but then you'll adjust the size based on that. This won't.
Wait, I got 46.
You gotta move it a little bit and then it'll move like. Cause my stuff.
This is so annoying. Oh my god.
There we go. Peter, shut up. So it gets higher now, right?
I did it.
Then you can adjust here.
How'd you get 45? What the freak? So it's not supposed to be 50?
That's not the point.
Oh my god.
Mr. Kenny, I got 41.111.
I know, but I wanted it off so that we can see the next part that's actually the most
I'm
important
so
part.
confused now. I thought we were supposed to be getting 50.
No, I said my challenge for you is to
You
get
can move it
both
around.
low.
If you're just, I didn't mean.
So basically I had about 50 levels under 50.
Tonight.
You're good.
Right here, 41.1 repeating.
I have 50.
My point is
That was like
that I actually want something a little bit more off, and I'll show you why. Okay.
Oh, are you talking about the movable line?
All right. Hey, priority. I need us to focus on the questions that I already asked you to focus on. I will point out they gave you a definition of a least squares regression line. What is that? So now it helps to look at the sheet.
My bad.
Minimizing the sum of the area of those squares, right? Serena, pause. Right now, the sum of squares is 57. Is there a better regression line then?
Yes.
So a regression line is just a model. A least squares regression line is well, it's the least sum of the squares, but what does that mean about the model? It is the
most accurate.
most accurate or best. It is the best model. Okay.
You want to start talking through the questions? Or?
Yeah, let's go through 5 through 8 and then we'll do the next little part together.
Alright, each of us, so what was the smallest value you could find for the sum of squares? Who got the smallest?
You got 43.
41.09, 43?
I got
Okay.
41.
Who got a higher-ish value?
I got like 50.
Okay.
No, not 50. I got 47.
Looking at your points, Serena, if yours was higher, how many points were above your line and how many points were below?
I don't know. I lost it.
And then, Peter, how many of yours were above and how many below?
you want me to count like the ones that had on the
I
line?
got 49.
Well, so what I told him, because he did have a couple that were basically on the line, I think you had 7 above, or 7 below, 5 above, and 2 on. Does that sound right?
I had 3
Is
on.
49 okay?
Sanaya,
No,
you're
I
missing the
don't get you.
point. The point is that we are just trying to find the best, the least
Well, I feel like
sum
I
of
was
squares.
yours. 3 on to the other questions.
You're missing the
Yeah, I
point.
had 3 on.
I don't need to have.
Serena,
No, you don't have to have a 41 to
I told you
answer
the
the
wrong
questions.
value.
Answer
What
the
is
This
it?
one
questions.
was 50.
But that's
What?
how
Like
many
my
questions
sum of squares is
Hold
50
on.
now. I
does
changed
anybody
it.
have a higher than 50? What's
Yep.
yours?
How you guys
42. What's
Okay,
yours?
I'll
Yours?
write down.
45.
Jaden, Serena, Miss Hughes
Okay.
needs to borrow you for a couple minutes.
Huh?
Miss Hughes needs
Right
to
now?
borrow you for a couple minutes right now.
Both of us?
Michael, what was yours?
I got 41.
Will you pull ours back in?
Yeah.
So we can kind of give us.
What do we do?
So ours was about 57, and we have 1, 2, 3, 4, 5, 6 above, 2 below, and like, so you say 1, 2.
That's 5 up there, so 5
7.
on. Or,
If there are 5 up there,
7
2, 7 on.
yes.
7 on.
So notice, there's a lot here that are on, but you see how we're not really balanced on what's above and what's below?
No.
And do we have as good of a model as Peter did?
No.
So what needs to be true when we're looking for the best model?
Above needs to equal below-ish?
We need to roughly split the data. Yes. We need to roughly split the data. That's all that we need you to see through.
So
Number 7.
what do you notice about this distribution of the data points around the line? What do we notice? When our
Like equally split.
when our
That regression line is like the least squares regression line.
right, when that value is lower, they're equally split versus higher, it's off balance. So to have the smallest sum, how do the points need to be distributed?
Evenly.
Evenly.
Roughly half below, half above. Evenly split.
Half above. Roughly. I don't think that's roughly in math.
It's approximately.
Yeah, same thing.
Yeah, close enough.
Alright, I totally can just figure that out. So now you're going to compare your line with the regression line that TI Inspire creates. So go to menu, analyze.
Let me
Oh,
just pull it up, sorry.
yeah. So you have menu, analyze, and then regression.
That might have been what I did.
So I will point this, yeah, he did. I wasn't gonna say,
So I
but
really did the best one.
Notice
right,
there's
no, I had a
MX
no.
plus B, but that is not the standard for statistics. That is just what is normally done in math. Statistics, we typically do A plus BX, which I actually prefer that one. Makes more sense. It's where you start the y-intercept plus what you're repeatedly adding by. That's neither here nor there. So notice that's this new line. You see how those data points are now below? And these are below, and then those are above, where Peter cheated. And so that model's a little bit better. And so we go to analyze, residuals, and
So that's like the smallest sum of squares it could be?
that is the whole point of the linear regression. It is the smallest sum of squares possible, so it is the best model. Yeah.
I also have an original one below.
Okay, so let's answer these questions.
Alright. Together or just have them?
Yeah, let's answer those and then let's just do 9 and then 12 and 13, I think. We can skip 10 and 11.
Alright, so what is the value, just kidding, we already know the value of the sum of squares on the actual regression line because it's 41.09.
Peter.
Because somebody cheated on the last question.
What are we talking about?
So, give it a 12, or give it a 13.
So skipping to 13.
So interpret the slope and y-intercept of this data's least squared regression line. So what is the least squared regression line that they gave you? I want to read it.
Negative 454.364 plus 0.26612
129.
Yeah.
All right. How would we interpret this?
I don't think we've done that at all yet, have we?
No, but I feel like maybe because like
I
Expected.
think let
We
me
did talk
set it
about
up.
we're literally right here.
Ish.
This is our.
Well, but what they're asking here is to interpret slope and y-intercept. So let me reframe this. What is y again?
Life expectancy.
Expected life,
Oh.
or life expectancy, right?
Expected life
I didn't know what you were asking.
Predicted life expectancy. That's what I'm looking for. What is x again?
The yield.
The year. And so what I just want to remind you is this is a what?
The y-intercept.
A y-intercept. What do you know about every y-intercept that's ever existed? The x is 0, comma.
I don't get, why is that the y-intercept?
What do you mean?
Because that's just the
Well-
y, right?
It is just y. Two things I want you to think about, Sprig. Every y-intercept we've ever looked at, the x is what?
Plus, if you like put 0 on that and multiply it.
That's what I was
it's
going to
just
say. For every y-intercept, the x is
Zero.
0. So what do you get if you put 0 in for the year? This becomes, what's anything times 0?
0.
0. So that becomes 0, and what are you left with?
0. That number.
Negative 454 plus 0.
0. But
What are you struggling with it?
that's not age.
Hold on to that, because we're going to talk about that. Yes, Sprig, that is 100% right. I'm glad you thought along the context. We're going to talk about that, but hold on to that. So this is my y-intercept for my, because remember, this is a what here?
Life expectancy.
A linear regression, a least squares regression line, okay? Which means that it is only what is? Predicted, right? That's what the hat means. This was predicted, okay? So from there, what is this then? The slope, and what is that slope?
0.26129.
And what is slope always understood to be divided by? 1.
That's what I do whenever I misspell
Okay.
something, I just write over.
So, I need y'all to remember this. That means this is, we want you to think through this, but think through 0 what? Negative 454 what? When we calculate slope, how do you calculate slope?
Change in y divided by change in x.
Think about that to be able to interpret what these numbers mean and what these numbers mean, okay? Come up with something for a couple minutes, we'll debrief, but we just want you to think about it first.
Life expectancy in year 0 is negative 400.
Write it down with your group. Talk about it with your group first.
I don't even know what I'm saying.
So,
Let's do this, let's just do y-intercept and talk about it in 1 minute. And then we'll have you do slope, because slope's a little bit more complicated.
Wait, are we interpreting?
Interpreting y-intercept,
Oh.
just the y-intercept. You literally almost already said it, Sprig.
So the
The life expectancy in year 0? That doesn't make sense.
It's still, there's a reason, so there's one thing you're missing.
Is everything
Based
good
on a
then?
really small sample.
So we're just.
We'll talk about that again as well.
Why are we leaving the most confusing stuff for the end of the year?
So do we just have to write like
Should
the
take
I thought we should
calculus.
started harder and then
Zero
way
is like
easier. I feel like I
very
would have
bad.
actually probably.
I miss probabilities.
Okay, Ms. Kolsky.
Alright, so
What?
what is the y-intercept telling us?
The life expectancy for year 0?
The life expectancy for year 0 is predicted to be
Negative 454.364.
beautiful. That's
I
Really?
just want to point out, yeah, that's 100% right. I just wanted to point out what y'all were missing is the idea of the predicted life expectancy, is negative 454. Not the actual life expectancy. That's unreasonable. That cannot happen. Peter, what were you talking about?
It's the same.
The life
It's a small sample.
expectancy
Hey guys,
for
what was the
years
lowest year we had?
is that number.
1890.
Was it 1890?
So why-
I thought it was 1900, but it might be 1890.
That was 1900.
It's 1900. So the lowest year was 1900, and the highest year was 2004.
I don't even know.
So we're going way outside of the data that we have. That's called extrapolating. Don't extrapolate
That's bad.
far outside of your data.
That's bad,
That, when you extrapolate, it does not make sense most of the time.
bad.
Then why
But-
Yeah, then why did
do
they do it?
Because
To-
it's still interpreting the y.
Yeah,
Mr. Kenny, I'm
so you
confused about this, like this specific thing.
What?
I don't understand, like, cause no, when,
This
like,
is
I
the-
understood until she said it, and I was confused.
All right, no, this is not possible. Obviously, this can never happen, right?
Right.
But the reason this doesn't make sense is what Mr. Kinney was trying to say, is our data points only go from 1900 to 2004. And now we are trying to go 1900 years earlier.
To 0 AD.
So if
0 years.
Mhm.
It does not make sense. You cannot extrapolate your data that far because it does not fall in line.
But if we did have data close to that, would it be more accurate?
Yes.
Yes, we had
So,
data
like-
year 1 and we're trying to
Okay.
figure out year 0.
So like
Okay.
1999.
So it's easier to figure out the yields that are like gonna be like closer than ones like super far away.
So, yeah.
266.
Extrapol is
Okay, so is this in like the
Yeah, because it
the
tells
life
you
expectancy of someone who's 0
Yeah,
is
7%.
negative point?
Not who's 0,
What-
because
okay.
our X is the year we're looking at.
it's
year
Yeah.
year 0.
In year 0,
Oh, okay,
yes.
okay, okay, okay.
And then what about our slope? How did we interpret that?
The life expectancy is expected to increase by that year per year.
Right. The life expectancy is expected to.
is it predicted to or
Increase.
expected to?
Does it?
What
Can
was the
those
question?
predicted or expected? Can those be?
I would say predicted. I would always say
Okay.
predicted. You can say expected, but predicted is the traditional term. I just want to point this out. Extrapolate, extra, to me means to go beyond or outside. Extrapolate is when we predict values outside data range. When you interpolate, you're predicting values
with it.
within the data range, so you're just plugging input in. I just want to show this. Not what I wanted.
Wait, would
If I were to, so this is 1850, right? Or 1950.
Yeah.
This is 1940. So could I make a prediction for 1945 and it'd be pretty close to what it probably actually was?
Sure.
So when you interpolate, your predictions will be more accurate than if you extrapolate. When you
Oh
extrapolate,
my gosh.
your data is usually, your predictions are way off.
What's that?
Hey, focus on stats. We gotta go. This thing is way too long.
All right.
I get it. I know it's the difficult part. And tonight I'll sit down and talk with you more about these things. Did you write down the interpretation of the y-intercept? So, I'll personally always start with my independent variable in year 0, in year 0, the predicted life expectancy is negative 454.364 years. I'll talk with you about it, Serena. Just need to point this out. One thing I do want to emphasize to make your life easier, I need you to remember this. Because of this regression model, this is year, right? So I label this with my variable. Label X or year. How would I label this though? But I would not label it Y because it's not the actual Y. It's not the actual life expectancy. Y hat or the
Expected.
predicted
Yeah.
life expectancy. That makes this make way more sense. So in the year 0, the predicted life expectancy is this. We need you to try to apply that to your slope.
Oh,
Yeah, because they haven't done it. Try to think about slope yet. I need y'all to try to apply this to your slope.
Apply the point.
We interpreted the y-intercept, right?
Yes.
I need you to
Interpret
use what we talked about to try to interpret the slope.
Oh, okay. I thought you meant like incorporating
The
the
life
point.
expectancy
Okay.
is predicted to increase by 0.266 every year. Right?
Why don't you write down what Sprigg says and let's
What'd you say, Sprig?
critique it.
The life expectancy is
Year zero.
predicted to increase by
Predicted.
0.2261229
Life expectancy. Zero.
every year.
Predicted life
But
expectancy
Peel says oil.
is this.
Okay, because the rain.
Is it every year or every 10 years?
It is.
No, not this, I'm talking about.
Well, is it divided by 9 or is it divided by 1 or 10?
I don't know,
Yeah,
is
the
it
one
divided by,
intersect?
it's divided by 1.
This one's supposed to be.
Alright, so
No, that
then
is
it's
right.
every,
I thought you said it was.
1 year.
1 year.
You're going where?
No, that is right.
Which
A
was the check?
plus
Year per year.
the,
You pay?
Yeah, I'm trying to
this
figure
is
out how
not
to
the
work
actual
that.
life expectancy.
Okay, so
That's just what is predicted.
Increase
Wait,
by.
can people live negative 450
Every
Wait.
years?
Don, do you?
Each
Yeah,
year.
each year.
Each
Okay.
year.
Have you met anyone who lives less than 0 years? Okay, so that's impossible. That's what we were saying. In the real world, that's impossible. But based on this model, that is still what the y-intercept is. Okay. That's how we interpret it still.
Can these be in negative ranges?
What do you mean?
Like, could the values like be negative and still be accurate? Like, could you use it for negative values?
Life expectancy. Say that one more time for me.
If I was saying like the net exports of a country, so like, shut up, Brandon. Like it could be like in the negative
Yeah, if it's
range,
decreasing.
right? And that you can still do that.
Net
with that?
exports.
Okay.
You would just say that it is predicted to
Expectancy
decrease by that amount
predictor.
every year. Okay, so this is a good start. This is how Sprigg said it, I'm guessing. Where's I need the eraser. No, you're good. This is a good start. This is how we would typically want to write it on the AP exam. So this is the change in y hat, or the predicted life expectancy. Notice how I'm again labeling it, right? One thing to always keep in mind, remember how we started with our independent variable here?
So
So when
dependent
I like to start with independent variable, and that is a normal thing. So one what? Year. So as each so for that's what it is. For each 1 year, is it increasing or decreasing?
increasing
How do you know?
because it's positive.
It's positive, right? Each 1 year increase, the what?
The life expectancy is expected to increase by 0.26629.
The life expectancy is predicted to increase by 0.266 years on average.
Oh wow.
You want to include that detail at the end. That one small detail is something that a lot of students miss out on, an E on the actual exam. That's why I wanted to add that in there.
Why do you need to put on
So it's like
average?
in the long run.
So it's kind of like in the long run, but the idea of a least squares regression line is essentially a mean for bivariate data. I want you to think about what I just said there again. A least squares regression line is essentially a mean for bivariate data. And so that's why we want to say it's on average. Because that's not how much it's predicted to increase every year, but on average, that's how much we predict the
That's
life
just what
expectancy.
everything
Oh,
is,
so
on
A-rock.
average.
Huh?
prediction.
So like A-rock instead of I-rock.
A-rock?
A-rock and I-rock.
Okay, moving on.
How do you predict the life expectancy of
Okay,
Americans
counts on
in
the brain.
2040 will be? And does this value make sense? So how are we gonna do that?
Plug it in.
Plug it in. Sorry. Substitute it.
2040 in.
And then. Tell me what you get.
Like 88.5.
What?
88.5.
88.5? Does this value make sense?
Wait, what year? 20 what?
2040?
Oh, I actually wrote.
Isn't it really like 80 something?
Uh,
I didn't.
What?
Can you restate the
82 for
question?
women and like 79 for men.
What do you predict the life expectancy of Americans in 2040 to be? Or 2040?
I got 21.
I got 60.
Okay,
Oh, no, that's
so
right.
did you use,
Y'all should die.
hold on, I'll put it in.
Guys,
I got
wait,
eight.
Prediction, like based off
I
my
got
own opinion.
No, I think it's use that.
2040?
You're supposed to use the actual,
Use that model that's up there, negative 454.364 plus
Negative.
0.266
oh my god.
Yeah, I got 80.
times.
yeah, you should've gotten 88.5.
Yeah.
So I basically put 1940 in there. Oh my god. Wait, what? I'm reading.
454.
Which one did
You
you?
know what I meant, so this is
Oh,
this
okay.
is Kowalski.
I mean, I'm just saying.
So in the equation, I put
Yes.
1940 and then
Because
the
it's the
same
year.
So use
Okay.
your old slope. That was it. So does that data value make sense?
Yeah.
Yep.
Something.
How about if I told you that the average life expectancy in the US right now is 77 years old?
I feel like that's too
Makes
long for
sense.
me. That's too long for me.
Perfect enough.
It
I just
makes
want to point out that in 2004 it was what?
Rather be that hard.
like 60 something.
What was the actual life expectancy in 2004? Someone please look.
70 something.
Look at the,
Oh, so it was 77.8 in 2004. It is 77.43 today. Do you still think it makes sense that?
I mean, it could. We don't know what could happen.
So there's extrapolation. We don't know what's happening, but guys, I need y'all to think about it. It was 77.8 20 years ago. 77.4 today.
so it's gonna keep.
Oh wait, this data doesn't.
Not necessarily. That's the danger of extrapolation.
It changes.
It's, notice, we're going outside of our data range, right?
Most data isn't lineal.
Yes, that's true.
So
So-
we have to do something within.
So we would have to collect more data to make a better prediction. I will be there in a second. We gotta move to the next piece.
Alright, so what's it, it's a
Yeah.
88.5.
I would say it doesn't make sense if the average life expectancy is essentially the same as it was 20-something years ago.
Wait, is that?
Well, is that in the US or in the whole?
Break to medicine.
The US.
About 5 years. To catch up.
Alright, alright, complete page 4 is practice.
Okay.
Next page, practice for you. Awesome.
Not today.
Not right now.
Okay. So what?
Alright, now we're going back to the Barbie page. We're just doing the notes on the back, right?
You gotta multiply before you can add.
Here's my Bobby.
What's your gonna?
Ma'am.
We're just doing the notes on the back of this one?
Yes.
Alright, y'all flip this over so we can have a place to have these notes I'm about to give you. So it's lesson 3.3, making predictions, the Barbie page. How to make predictions. So, what, how do we make our predictions? What do we use?
So it's
Y hat is
like I had the right
equal
idea, like right now.
A plus BX.
to A
No, you
plus
gotta fix
BX. Now, be cautious with what? What were we just talking about?
Extrapolation.
Extrapolation. Beautiful. Alright, where A is our what? Y-intercept. And B is our?
Slope.
Alright, how do we calculate residuals?
Oh, actual minus predicted value.
Actual minus predicted. And we can do the R A minus P or R Y minus Y hat. When we interpret it, the actual, whatever your context is,
So you're gonna write context, right, Brady?
You're never gonna let that go.
This
There.
joke is going way too long.
Yeah.
It's
and then
getting
your
crazy.
residual
You say it's going way too long, but are any of you going to forget it at this point?
above
No, but it's still cringe.
Yeah.
being drilled on me now.
Good.
Wait, you said right context?
What does that word say?
I can't see what you're writing.
I can't either.
How can I write it and then stuff
Well, I
like
just feel like
there's
if
like
you
no
was
other
writing
way
on
for
B,
me to write
I'm
it.
saying because if you was writing on B, like you don't see.
Value for x equals
I'm not used to sitting at this table, okay? I can usually see
I
what
can't see crap.
Just give me 5 minutes.
By the way, hey guys, when is the actual going to be above the predicted value?
When it's positive.
When you have a positive residual, it's gonna be
Dude,
below
move
when you
it.
have a.
Negative.
The hair just like increases the like block.
I think we should put another
Okay, you said
limit
that
on where
issue.
Jane can sit and put them always in the back of the classroom, because this is insane.
How about we focus on the next section?
So when we interpret, when we're interpreting our y-intercept, we're gonna go when
That's better.
the x equals 0 context,
I'm just gonna put that.
the predicted, I'm gonna move in a second guys, don't worry. The predicted y context is y-intercept. Does that make sense?
Yeah.
Okay.
No, because you were
So,
under
like in the last one, when in year 0, the predicted life expectancy is negative 492. So, and then for each, they have for each additional life context.
Yeah, which is for each 1 year increase,
Yeah.
right?
Like, yeah, you have to have context for each
Why
X.
can't you just say each year?
You could, but it's not always gonna be each
What do
year.
you
I know
do
it's not
now?
gonna be one all the time.
This is 0.
X
Well,
equals
actually, the
0
denominator
context.
will
So whenever X is
almost
0,
always
whatever
be
that
one,
context is.
but what I'm saying is not always gonna be 1 year. For instance, like if we looked at the candy grab activity again, the 1 centimeter predicted, for each 1 centimeter, the number of candies grabbed is predicted to increase this much, right? So it's for each additional, whatever the X context is. That's why we're saying that. You can reinterpret it a slightly different way as long as it maintains that idea.
They don't have this in there.
Put it in there.
That part. No, I know, I did.
Oh, know what it is? I remember how I usually like to word it. The predicted Y context typically increases by slope.
Okay, so you either say typically or you say on average?
Correct. Yep. One of those two. Typically
Yeah.
increases or decreases by that slope.
This next one is what you wanted to do.
Okay.
I'm pretty sure. Because you were just like quickly talking about how that works.
Yes, that's
Yeah.
right. That's right. Okay, I do want to point out, when talking about the life expectancy, what would be the form of that data?
Years.
The form?
What does,
In
what,
years.
what? Form?
Like when we're talking about
Uh-huh.
form,
Never mind, I think.
Direction,
Oh,
strength, and form.
Lineal.
moderate,
I want y'all to look again.
bruh.
So,
Do you really think that data look, can I erase this? Do we all have it?
No. I can say
You're good. Look at it on your calculator. Does that data really look linear?
Kinda.
I
mean, it kind of fluctuates up and down.
It looks-
Stays
So,
zero.
it- But it kind of is curved around it, isn't it?
you might have to
Okay.
read it off of hand, right?
So let me do this really quickly.
Oh, interpretation.
Everything is long,
So menu, analyze. I want you to look at residuals and show residual plot. Just look up here for it. Okay. So this is a residual plot. Okay. What do you think each of these data points represents? A residual plot. So it is the.
The residual?
It's the residual. Yep. It's the distance the actual is from the predicted. Look at it. Look at the residuals. The residual plot helps make it easier to see. There's a clear pattern there. The fact that there's a pattern in the residual plot means that that data was not really linear. Can we use a linear regression to model it?
Yeah.
Yes. In fact, I want us to quickly look at what the R value would be. So if you ever want to do calculate an R value, you go to statistics. Any guesses from there? Can I erase now?
Yes.
Okay. Where do I go from statistics to calculate the R value? Stat calculations. There we go.
Linear regression.
And then Oh yeah, linear regression, that sounds good. X list, that's my year. Y list is person's life expectancy.
Wait, which linear regression?
A plus BX is typically what we use, okay?
Yeah.
And then I'm gonna put the first result column in, I think D. So it's gonna actually save your regression equation. I'm gonna come back to that in a second because that's actually really powerful and I forgot that we would even want to do that.
Is it A?
Ooh, hold on a second. I need it to be E for the,
Wait, what's going on?
Wait, I'm lost.
Yes.
You gotta go up a little bit.
guys, put in your variables under X list and Y list. Year, person. That's it. That's all I've done. And then first result column goes in E. Three things. And then after that, you hit OK.
Okay.
The reason I had to do E is because I remembered that the last set of data was in D and I didn't want to overwrite that. Those numbers look familiar?
Oh, yeah.
Yeah, darn straight. What does that R squared mean? That's my coefficient of determination. 97% of the variability in the life expectancy can be predicted by the regression in respect to the year. That is based on what we talked about yesterday. 97% of the variability in the life expectancy can be explained by the linear regression with year. Okay, what's your question, Brayden?
I'm doing exactly what you're doing, but I'm just giving you the data.
Year. That's fine.
Yeah, it's up there, isn't it?
I mean, it's up there, but hold on. Oh, that's because you're in the wrong, you're not,
Yeah, it's up there.
yeah, yes, oh my gosh, alright, guys, you gotta be looking at the right rows. Okay, anyways, there's R, what is R telling us? Hey guys, what's R telling us? The correlation, but what would that R tell us?
If it's strong,
So it's a very strong, positive,
linear.
Well, non-linear.
but it's non-linear.
Wait, how do
So
you-
this is where we have to be careful. The calculator can't tell if it's non-linear or not. You have to use your eyeballs to look to see if it's non-linear.
Go back to the.
Can a correlation be really strong, indicating a strong linear relationship, and it's not actually linear? The answer is yes, and you have to be very, very careful about this. Based on this correlation, I would say it's a very strong linear relationship. But when I look at the residual plot, does that indicate that it's actually linear?
No.
No, it's curved around it. If we want it to be nonlinear, it needs to be scattered. For it to be nonlinear, this line, when we do our residuals, should take the shape out of it, and this is what we would want to see. Notice how those data points are now fairly scattered. There's no pattern like there was here. Now it would be scattered around. I could not draw a curve through my data points.
So R tells more about the pattern than if it's linear.
So R tells you the strength of the linear relationship if it's linear.
If
If it's not linear, you can't really use R very well.
okay.
And so we need to be able to look at a residual plot. You need to be able to look to see if there appears to be somewhat of a curve or not.
So if it's
I'll upload a
scattered,
video, say again.
if it's scattered, it's linear.
If it is scattered on the residual plot, it's a linear relationship. Okay? Because when you subtract out the predicted values and you get just the residuals, you've taken the form away. And so when you take the form away, it should just be scattered. Let me say that again. Thank you. Actually, I'll put it in the end here. So, again, here is where we have to be careful. Does that line get pretty darn close to those data points?
Yeah.
But when I look at those data points, does that appear to actually be linear?
No.
No. Definitely does not appear to be linear, and that's where we need to be careful. If I do an R value, I can almost guarantee you it's going to be a pretty high R value, high correlation coefficient.
Oh, yes, sir.
But we have to use our eyes and recognize that that is not a linear relationship. Do I need something?
Brad needs to speak to you, and then you need to answer your email.
Who? Jaden? Like right now or
I
after?
don't know. He just said, I need Jaden to answer his email.
But he needs to speak to me?
Yeah, whenever you get a chance.
Okay.
Oh.
Alright, so describe the form of the relationship.
Again.
Wait,
What would be
so
the form of this relationship?
on the monster.
Non-linear. Yep, the monster energy. Guys, it's the very next lesson. 3.4. We're not on the outliers. It should be right after. Okay.
So
The form is
non-linear.
non-linear. There we go. Could we now use this regression line to predict the stock price for 2010?
Yeah.
Can we find the residual? So we have already done this lesson in the form of the squared up task. Okay? If you want more practice with this, then this is a good task to work through. I will upload a video. Notice you find your prediction, and then how am I going to find the residual? Actual minus predicted. That's it. Okay? So substitute 2010 in for x, then do actual minus predicted. Alright, so, yep, already covered all this. Okay, so least squares regression line. When I look at this and I want to make some notes, what do we need to know about a least squares regression line? By the way, sorry, LSRL, that is least squares regression line. And so earlier tonight when you were all stressed out about, oh, I didn't have the best whatever, no, you weren't expected to. We wanted you to see that we are trying to minimize those sum of squares, and what actually minimizes those sum of squares? The least squares regression line, okay? Alright, so least squares regression line minimizes what?
Sum of squares.
But what squares?
Residual.
Some of the residual squares. So remember, what they're literally doing is taking the residual and squaring it. Yes, Serena?
What is a residual? Like, I kind of get it, but like, can you explain it? Like, you know what I mean?
No.
Oh.
Right here.
Oh, I think she was going to wrongly interpret it.
Right here. So here's my actual data point. Here's what was predicted. That's my residual. The actual y value minus the predicted. Okay? So a residual is just how far the data point is from the prediction. Okay? Now what I need us to recognize from here is that, and this is what I should have said earlier, any guesses what the sum of just the residuals would be if I look at all the residuals on the least squares regression line?
Wow.
The sum of the residuals would be?
0.
0!
Because you want the above to equal the below.
Right. Just like with what? That we've already studied.
Give it to him.
Assets and liabilities.
Well, yeah. When we studied standard deviation, we couldn't just do x minus x bar because the sum of all those deviations would have been
Negative. Zero.
would have been 0.
Yeah, you're
so
right.
what did we do? We had to
Square
square it. Then we divided by n minus 1. I'll talk more about that later. And then we had to undo all that, so take a square root, right? So why are we looking at the squares here? Because the sum of that would be 0. So what do I need to do?
Square it.
Square it to make them positive, and I'm trying to find the least sum of squares. Okay? That's what we're trying to find there. Does that answer your question, Serena?
No.
Okay. So it minimizes the sum of residual squares or squared residuals. So what is a good residual plot? If we graph our residual, and I will say there are negative residuals and then there are positive residuals, but my graph looks like this. Does that mean I have a good model? No. So this is bad model. Okay? Let me see, we got another example here.
That's also
Is that a good or bad model?
bad.
Pretty good, I guess.
I don't know, y'all.
The fact that it's expanding out like this, there's a pattern there that I don't want. That's a bad model.
Oh, so you just don't want patterns?
You don't want a pattern in your residual plot.
But what if you see patterns that aren't there?
What if they're?
Yeah.
It will be clear, y'all.
You see things.
It is okay to have a little bit of a pattern, but notice, you see how those data points are pretty darn scattered around.
It looks like a
Looks like
square
a
to me.
pattern.
Yeah, it looks like a square.
It looks like
Or like a rectangle.
Guys,
It looks like.
that is the definition of no pattern.
Wait, what's a good pattern? What's a bad pattern?
Confuse the enemy.
That's not a pattern.
Or maybe it's like a straight line. I see like a straight line, kind of.
Guys.
Like if it goes down.
Literally, half the data's above, half the data's below, and you can't predict how far above or let's say it that way. You cannot predict how far above or below a data point's going to be at all. Here, I know that as I get further away, my residuals are going to be larger or
So
smaller.
is the last one good?
This is a good model.
Okay,
This
so
is a linear, and this isn't just a good model, this would be considered a linear relationship. There is no pattern. That is the definition of no pattern in a residual plot.
I think you guys are.
Yeah, because that's definitely a pattern.
Dog, there's no way to predict, listen, okay, right here. This is close, right? And one of the data points is really close to what was predicted, and one data point's really far away from what was predicted. I move a little bit further away, and this data point's pretty darn close to what was predicted, but this data point's really far away from what was predicted. So is there a pattern there, or does it just kind of magically appear somewhere?
It's not like a box pattern.
I mean, overall, like if
Stop talking. Go read the textbook. Learn. Frick, there is no pattern there.
Frick.
Can we start like walking around?
No.
Where did he go?
Are we doing?
So guys,
Really? Look at
Valley
the film.
crashed out.
do we have this?
Yes.
Okay.
That was like the very last one.
That's not a
So,
bad word.
I'm not going to go all the way through it, but I need us to recognize this. Right here, when I look at this data, is that somewhat scattered? Or can I draw a curve to approximate that data?
A curve?
Like,
Wait, where is
It's mostly scattered. Like, if I wanted to try to draw a curve, it would not work out very well.
Oh, we're talking
Like-
about residual?
So, either one. So, if you notice, the residual basically kind of looks like we just
Oh, okay.
rotated this horizontally. Okay? But when I look at that, there's no real pattern there. It's fairly scattered. Some are close, some are far away, but there's no curve to it. There's no, it's patterning out. There's no pattern there. So is that going to be a fairly linear relationship?
Sure.
Yes, that's linear. Okay. Now, oh yeah, so I needed to talk about this mini tab output. That's why I wanted to look at this, right? That's what it was. All right, so a couple of things I want us to talk about right here. Okay. Any guesses? And so look at your sheet. Any guesses what these things mean?
Coefficient, standard
So let's
error
back- let's-
coefficient.
Oh, so coefficient, standard error of the coefficient.
True,
True
false.
value.
It's false.
What'd you
Wait,
say,
that's a
Serena?
P.
True value.
Not true value.
T value.
Oh, like it.
It's a what?
Value. T.
T standardized test statistic.
Oh my goodness.
Oh my
Give me a break.
god.
P-value.
I thought we were over
It all
this.
goes
We're not.
Fuck, we should have included words.
Okay. That is a T standardized test statistics. What do you think P stands for?
P-value.
Oh, that's a p-value. We will learn more about those later parts, but what I need us to focus on
Hypothesis,
is just this right here.
is that like
Okay?
unit 9?
So, say again.
Is it like unit 9?
It's the very last thing we studied, yes. Coefficient, so is that 1.151? Yes. So 1.151 is the coefficient for the what? Constant. When I look at y equals a plus bx, where's the constant? A. So that's just A. That's it. This 1.469, that's the coefficient for the what?
City fuel economy.
City fuel economy, miles per gallon. So that is B, because notice this is my x, or independent variable. You can clearly see that right here on the x-axis. So from that one little table, I have my regression equation. The predicted, what's my outputs?
City fuel economy.
Not my predict, no, it's not my outputs.
Highway, fuel
Highway fuel
economy.
economy.
There we go, predicted highway fuel economy, you can just put Y hat. But the predicted highway fuel economy equals, so remember, predicted outputs equals, what is A? That's my constant. So 1.151. Then what comes next? Plus 1.469 x. But what is x again?
The city fuel economy.
City fuel economy.
So what is,
Okay, could you put an x there? Yes, could you put a y there? Well, a y hat. Here, could you put a y hat?
Oh, yeah.
Yes. I like putting the context with it though. But we just need to recognize that these coefficients are the coefficients for the constant, which means it's just the constant. This coefficient is for the independent variable. The coefficient for the independent variable, that's my slope. Annotate that table to find y-intercept and slope. Serena, you look like you got a question.
I just need to figure it out.
Okay.
Everybody
What
pull around.
parts do you need to figure out still? Okay, can you stay for a couple minutes after class so we can talk about that a little more? Okay. So if I were to describe the relationship, what key things would I need to talk about with describing this relationship?
Strength.
Strength, direction, and form. So what would I probably call this?
Weak.
Don't look at the
Well, let's
residual
stop
plot,
this.
look at the scatter plot.
It's like
What?
moderate.
What are you talking about?
Don't we need an R value?
To be precise with it, yes, but just looking at it, what do we think it is?
It looks weak.
It doesn't
How
look.
do you get weak?
Okay, looks
I mean, it look.
That is a strong, positive linear relationship.
Really? It does not look strong.
Yes, that is strong.
No, because like there's still points that's kind of far away a little bit.
Listen,
A little bit.
listen, that's a strong positive linear
You
relationship.
talking about the one on the left?
We will get R values to be more clear on it later, but like, if I take this line away, is that linear?
Yeah.
Okay, it's a strong linear relationship. Like,
Very strong though.
I understand what you're saying, but like, it would need to be, it would need more data points further away. Like this would be a moderately strong linear relationship. Okay? Got it. And I understand that we're not 100% there yet because y'all are just now seeing this and we're moving somewhat quickly, but I promise you that's a strong linear relationship. Like, it is.
On everybody's level.
What?
On everybody's
No,
side.
no. It's gonna get a lot of fish fry.
Ms. Kowalski, you ready? I would just go through this together. We don't have time to.
Are we still running?
Apparently, we're not going to get there today. We'll get there tomorrow.
It rained only anyway.
Oh,
Oh,
good.
yeah.
You
This
do
is
it
next
inside.
Oh yeah, my shoes are wet.
We could do it inside, Mr. Kid.
No, we do it inside.
We do it
Why?
next
Regardless.
Wait,
No,
so
I'm
what
gonna
does
do
it
it
involve?
Friday
What does it
because I'm gonna do
You'll
it.
find out tomorrow.
Jake, you're not gonna get it, bro.
I'm gonna do it, so.
What if I'm gone tomorrow?
Can you please chill and let us
Do we
teach?
have this?
Yes. Wait, are you seeing who's fastest?
.com. No.
Maybe it's like leg length versus speed.
Mr. Kenny, can I use the restroom real quick?
No.
Dude,
Alright.
Keegan told me yesterday.
Is that a for real no or?
You can't hold it for 15 minutes?
Then no, because that means I have to hold it for another 45. So that's an hour.
We gotta learn how to.
This is, yeah.
Apparently that means.
Oh, we're supposed to put our own
Yeah,
data
we-
points?
Fill in the A and B and C and D.
Was that a real no or a fake no?
Just go use the restroom, why don't you?
Alright.
Alright, so,
Oh, I thought you
yeah,
were gonna
no,
do it.
you're good. There we go.
Oh. Alright, this is the next page, how do outliers affect the LSRL? Oh, no, it's plotted another page. Alright, so, we are using this applet. We're just gonna do it together. We're not all gonna do it, one at a time. So, predict if the slope, y-intercept, and correlation will increase, decrease, or stay about the same when we add different points and then take them off. So the first point we're gonna add
It's like right here.
is gonna be right here, don't add it. What do you guys think is going to happen?
It's gonna make it legal.
Okay,
Sorry, I'm just trying to get that.
so our slope will what? Increase or decrease?
Decrease.
Decrease. Our y-intercept will increase or
Um,
decrease?
Increase,
Yeah.
Increase, and our correlation will
decrease.
decrease. Let's see if you're right. Oh my god, that's crazy. You guys were right. Alright, the next point we're gonna add, we're gonna get rid of that one, and now we're going to add this point. Now what do we think is going to happen?
Uh,
Increase.
Why is it decrease?
Y-intercept
Y-intercept
Hold on.
increase.
No,
No,
what?
no,
It-
no, 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 no.
Well,
What?
What
Increase
is?
can be
I mean, it might
What?
increase a little.
It might increase.
I feel like it would be
It's
increased because it's higher,
Yeah.
so
Increase.
yeah, the slope would.
Increase.
This
Okay.
is the
Well,
point
like
higher.
it's being tilted.
Yeah.
Yeah, is it being tilted or is it being
Same
Or
thing.
decrease?
Is this what?
Right?
Decreased.
So now the slope did what?
Increase.
Decreased?
The slope decreased, sorry, I was putting my finger on
Wait for B.
the y-intercept
I don't even
increase, yes, this is for B. And then our correlation,
decrease.
Here, let's do this point
Wait.
here.
Oh,
Let's do this. This will be closer to what I want.
oh, that's D.
Oh, is it?
It's working its way around.
Okay.
So like now we're adding a point right here.
Wait, what was the stuff for B?
Decrease, increase, decrease. Alright, C, adding the point C right here.
Oh, we were supposed to be writing this.
What do we think? Yeah. What do we think's gonna happen to the slope? Okay, what do we think's gonna happen to the y-intercept? And correlation? Alright, let's see what happens. Because we all have different.
Did they
ideas.
just all decrease and increase?
So,
I
we remove the point.
bet it's used for the
What? Here, you
It's
can't see
be
it.
directly under this one.
That's
What is
not-
it?
yeah, should go there.
It's directly.
Y-intercept decrease.
Oh, hold on.
Right.
Yeah, that's what we're wanting.
Alright, so this is where we added the point. Alright, so here, our slope stayed the same, our y-intercept did what?
Decrease.
Decrease,
Our slope is the same.
and then our correlation,
Yeah. Look, so you see it, Serena, you see how that slope is roughly the same?
we're gonna talk about y in a minute. Alright, and then our correlation did what?
Decrease.
Decrease. Beautiful. Now, we're adding a point.
Yep.
Right here. What do we think's gonna happen?
Slope stay the same, y-intercept increase and correlation decrease.
Awesome. Let's see if Sprig's right. Oh my god. Sprig, you're right.
Wow.
So same increase, decrease. So points A and B there, they tilted our line, while C and D did what?
Did not.
What'd they do with the line?
Moved it.
Moved it, shifted the
Oh my
line
God.
up and down.
Speaking transformation.
How?
Why is it?
What was
Same
it?
thing.
The
was A?
opposite
Decrease,
command
increase,
is shifted by.
Um,
I don't even know.
alright, which, okay, but, so I'm confused on how I can work three because we're not flying.
Loras. I love
Yeah,
Loras.
okay.
Loras is my favorite.
Yeah, because we're going.
I like the
Yeah.
Phillips curve.
Boo.
Don't like it?
Okay,
No.
so
That's my favorite graph.
B, this is where we're gonna vary a little bit from the language Mathematica uses here, but they don't use this on the summary notes on the back, do
I mean,
they?
they kinda do, we just changed it. 'Cause
So it'd
they-
be more in line with the textbook?
Yeah.
So, okay. So which of these points, A, B, C, and D, do you think we would consider outliers?
A and B.
A,
B, C, and D.
you think all four of them?
Because
And that's
the
kind
table
of
says
what
it.
they're implying here. I'm gonna come back to that in a second. Why do we think they might be outliers?
Because they shift the y-intercept and correlation.
They significantly.
Now,
shifted.
I do want to point out, every data point will somehow affect the slope and the y-intercept and the correlation. So why did this one affect it so much?
Because it's all the way out there.
All the way out there, so it's, when you say out there, what do you mean?
It's like super far from the line.
So are you thinking vertically?
Both.
What it really is though, I want you to notice, like, that's where the last set of data points are. So that's pretty horizontally far away from the rest of the data, right?
Yeah.
This data point is pretty far horizontally from the data.
Uh-huh.
And we call those
Those are
influential,
influential.
influential observations.
How can you tell it's that? Like,
You remember how
Can
we
you just-
first learned to say that the possible outliers,
yes.
possible influential observations. But influential observations are when they are horizontally far from the rest of the data.
What about Peter's horizontally challenged?
Oh.
So can you be vertically?
So you're saying that he's skinny because he's not
No.
is that what you're saying?
No.
That's what I heard.
Yeah, your joke's bouncing.
So what are we gonna call C
I'm
and
gonna
D?
kill myself.
That's
Oh,
on
those
camera.
vertically fall from the rest of the data?
And so if they're vertically far from the rest of the data, we're gonna call those
Why are you looking at me like I know?
Outliers.
outliers.
Are
So
you specific about, like, the fact that they're,
potentially. Yeah, so these are, we will never actually quantify if they actually are, they're just potential.
So there's no
Outliers.
like equation or thing to check.
I mean, I feel like if it's like absolutely insane, you could assume.
Unless you actually learn how to calculate it, don't.
So there is.
Yes.
We ain't doing all that.
Is that for APP
It's the calculation for everything.
statistics?
So notice, I will say this, I do change it to vertically far from the what?
Prediction.
Prediction, which means it has a large what?
Residual.
Yeah, there we go. There we go.
Those are basically something to give up.
Yeah, basically.
yeah.
There's only one other thing to add to it, I think.
Saw me out.
Alright, so outliers, in this case, we are talking about what?
Horizontal, no, vertically far from.
Vertically far, so vertically far, they are out of pattern. Which means they have large or small residuals. Large residuals. High leverage is going to be very large or very small x values.
Yeah, so I flipped that. That should say high leverage for horizontally far from the rest.
What?
Influential observations are outliers or high leverage. That's what I was looking at. I was like, I think I flipped that.
Can I show them right this or?
You say high leverage?
I would just, let's erase this
Oh.
and put high leverage here. Outliers and high leverage are influential observations.
Miss Cole, she's right.
What?
Where it says leverage in purple, is it just leverage?
High leverage.
Okay.
High
I knew-
leverage,
I knew
sorry,
there
there
was
some
something
big
like-
heads in the way.
It's not
Alright.
big. If that makes sense.
Influential observations. If they're removed, what does it change? So like if we flip over to the other side, what happened when we removed A and B?
It would
Or added them.
change the correlation and the slope.
Yeah,
Change
what
correlation, slope, what else?
Strength.
The
And
y-intercept, and even the coefficient of determination. Because if it's going to change r, it's going to change r squared.
Yeah.
So they're like keystone species.
Alright, so, alright, so, hold on. High leverage.
I mean, it's just,
So here, these go in learning target 1. Are we saying this is high leverage?
Yes. that's also, I think,
Influential. Well, so these are here.
right, but it's how they affect the least squares regression line.
Oh, yeah.
Yeah, I was going to say, because high leverage
So high,
mostly
yeah.
affect the slope, outliers mostly affect the y-intercept. High leverage affect the slope. Jaden, that's adorable.
Huh?
You're here.
Why?
Kinda blocking the
Oh, you got
That's been there for like.
Oh,
ew.
He's racial gerrymandering now. Peter, he's still racial gerrymandering.
Serena.
Cause you have the room.
You did say your head was itchy.
Hey, guys.
Alright, and then formulas for the least squared regression line. What have we been talking about?
The A plus BX.
Okay, A plus BX, yep, so I've been talking about all day.
We didn't talk about these. Do you still want to like put them in there?
Hmm?
V equals Y bar.
Yeah, no, I think those formulas are done.
Okay.
Oh,
Alright, that's it. You don't need
So-
Wait, when you say that's
not to like.
They're not necessary.
just the
They never actually show up on the
Oh,
AP
yeah,
exam.
that's-
These are the formulas right here that Ms. Kolsky is going to refer to. That- What do we mean by Y bar here? The average Y is equal to A, your Y-intercept, plus B times your
Wait, okay.
X average or X
Y
mean.
bar is average, Y hat is predicted.
Correct.
Okay.
And then the B is equal to your correlation coefficient times the standard deviation of Y divided by standard deviation of X. So it's on that formula sheet. I'll point this out. If you notice, the reason why that one formula works is, what does your least squares regression line always go through? Can anyone tell what?
The origin.
No,
No,
that's
the
the
y-intercept.
mean X and mean Y. This right here is your mean X value. This right here is your mean Y value. And so your least squares regression line has to go through the mean of X and the mean of Y. That's where those formulas are coming from.
Oh wait, so your y-intercept is.
So that's not the coordinate plane, guys. That is the mean X and mean Y lines. There's your graph. This is Y X bar right here. This is Y bar right here. So average X and average Y. Okay. We've got 3 minutes.
Yep.
Again, I'll have to upload videos covering that. Okay, so we're going to talk about transforming really quickly. I actually already mentioned this. This very, very, very rarely shows up on the AP exam. So I'm not going to stress about it for the test. Like the test we're going to have on this unit, we'll review on it later.
She's here. Do you have me to go?
Yeah, go ahead. So we can see in this residual plot here, is a linear relationship actually a great prediction in this case? For me, I'm looking at it, it's not terrible, but there's a bit of a pattern there. At least that I'm seeing.
You could say the same thing for the other ones, I feel like.
Okay, you can say that if you want.
And you're
Like the one we looked at earlier, it was like the same.
Okay?
You're wanted.
By,
Miss Beth?
okay.
Because Miss Williams has a doctor's appointment.
Trouble.
Okay, no, we just have meetings for interns. All right,
Allegedly.
so, yeah, you got me. So, when I look at this, that is not a truly linear relationship. If you already have a linear relationship, to make it linear, you don't have to do anything. You just graph X and you graph Y. If it's exponential, what did we say earlier is the inverse, or a logarithm, right? But we're going to keep X, and we're going to graph the natural log of whatever your Y is. So you'll take the natural log of every Y value, and that will make it more linear. And then for a power, that means x squared, x cubed, x to the fourth, you're going to do a root.
Watch this be like,
Root of Y.
won't this be like one of our FRQs and you just didn't
God.
fix it and then like we fail?
Please stop. All right,
He does it same
What about
way.
like trick?
He's scared.
we do not do trig at all. We don't really do transformations like this either. We'll pick back up with that tomorrow.
Okay.
BYU will probably be Friday.
We're going upstairs. We're tired.
No, I'm good.
Oh,
I can wait, it's okay.